Hi, and welcome to Dr. B's AP Chemistry webcast. Today, I'd like to talk about drawing Lewis structures. This is a really important skill that all AP Chemistry students, in fact, all chemistry students at every level need to master. I'd like to give a special shout out to Michelle, Angela, Ivy, and Sierra. They're former students of mine, all off in college now and being very successful, and they helped me put this PowerPoint together. Here's what I'd like to accomplish in this webcast. I want to show you a process for drawing Lewis structures. There are some steps we can use to help us be more successful with drawing them correctly for both molecules and polyatomic ions. And although there is a little bit of guess and check with this, there are still guidelines to help us, and I want you to know them. We're going to do a lot of practice problems. All right, I'll try to draw them neatly. The tablet's kind of acting up today, but it'll be fine. And we're going to focus mostly on structures that obey the octet rule, but there are exceptions to that, and we'll talk about what we mean by the octet rule. But the exceptions include things like expanded octets. What do we do if we have more than 8 electrons around a central atom? What do we do if we have an electron-deficient species with less than 8 electrons around our central atom? What do we do when there are odd numbers of electrons? This is a rare situation, but it can happen, and I want you to have heard about it. So let's start really with the process. The first thing I always want you to do when you're drawing a Lewis structure, whether it's a molecule or a polyatomic ion, is to count the total number of valence electrons in that species. In case you've forgotten, you can find the number of valence electrons by either looking at the group number of that element or the group number minus 10 for your P block elements. It's going to be a number between 1 and 8. Okay. So if we think about methanol, CH₃OH, and I wrote it that way because I'm trying to communicate some information about the what's bonded to what. The carbon atom, a group 14 element, has 4 valence electrons. Each hydrogen atom has 1 valence electron each, so that's another 4. And the oxygen atom has 6 valence electrons. So altogether, 4 plus 4 plus 6, that gives me 14 valence electrons total to play with in the molecule. And I want to keep track of that because it's going to be really handy. I want to make sure that all 14 are in my molecule and that they're represented correctly. The other thing that I want you to keep in mind is it's not important where the valence electrons came from. I want you to not think about that and really focus on how many you have. Otherwise, it tends to lead to problems with drawing the structures. All right. Next, you go and set up a skeleton structure. You try to think about what atoms are bonded to which. And there are some guidelines to help with this as well. If you have carbon, it's probably going to be in the middle. Or your least electronegative element might be in the middle. If you have one of one kind of element and several of another, the singleton goes in the middle. Hydrogen is usually on the outside of the molecule. Halogens are often on the outside of the molecule, but if they're the singleton and there's multiple copies of another element, it is possible for halogens to be the central atom as well. So let's think about this in terms of methanol. We were starting to talk about that structure. Okay. So I can put carbon in the middle if I want to, which is really handy. And then I could put 3 of the hydrogens around it. Remember, it was written CH₃OH. And that's because I wanted to show that an oxygen is bonded to the carbon, as well as 3 of the hydrogens. And that 4th hydrogen is actually bonded to the oxygen. So this is my skeleton structure. Okay, so the other thing you're going to do is put the valence electrons into the molecule so that every atom has a stable octet. Well, that means it's got use of 8 electrons. A single bond where 2 electrons are being shared. Both atoms can claim use of both electrons. Sometimes we have unshared electrons. You count those individually. But everyone's trying to have 8. That's what we mean by a stable octet. However, hydrogen's satisfied with 2. So we can talk about the octet rule, but hydrogen's got 2. And we can count on carbon, oxygen, nitrogen, and fluorine always obeying the octet rule. Other atoms, it kind of depends. So we try to follow the octet rule and give everybody 8, either through bonds or unshared electrons, but sometimes it doesn't happen. We can use multiple bonds, so we can have double bonds, which are 2 pairs of electrons being shared between 2 atoms. We can have a triple bond with 3 pairs of electrons being shared between atoms, and this all works. The other thing to keep in mind is that when you're drawing bonds, I tend to draw them as lines because I think it's easier and neater. You will sometimes see bonds just shown as 2 dots, 2 electrons being represented there, and that's also okay. All right. You do also want to make sure that all your lone pair electrons are represented in your molecule. You don't want to forget to put them in. They need to be in the species somewhere, wherever it's going to give you the octet. They can't be left out. The structure is not complete without them. And you really want to double check at the end that all of your valence electrons ended up in the molecule. You kind of have to count. You really do have to count. So let's go back to methanol, which is what we had been drawing. And let's draw that again. All right. I'm not really fond of that red. I'm going to go to a blue color. So we had already said for our skeleton that carbon was in the middle. We had 3 hydrogens around it. And then we have an oxygen atom bonded to the carbon and then a hydrogen atom bonded to that. And we also knew that we had 14 electrons to play with. So I'm going to start by drawing single bonds between the carbon and the hydrogens. So a single bond, that's 2 electrons, another single bond, 2 electrons, a third single bond. So that's a total of 6 electrons that I've put in. Starting with single bonds is never a bad idea. So I can have a single bond between the carbon and the oxygen and a single bond between the oxygen and the hydrogen. And if I count, I have 2, 4, 6, 8, 10 electrons so far, but I need 14. I'm looking at my hydrogens, they all have use of 2, right? That single bond with 2 electrons in it. They're set. The carbon has 4 single bonds. That's a total of 8 electrons. Carbon is set. The only one that's not done really is the oxygen, which only has 8 valence. Or it should have 8 valence electrons, but right now it has 4. But I've only put 10 into my structure. So I can do a lone pair and then another lone pair on my oxygen. And if I count, I've got all 14 electrons. I've got an appropriate structure, and we are good to go. All right, so let's do another problem. Let's extend this a little bit to polyatomic ions. The basic process is the same, but we do need to keep in mind that I have a charged species now. Okay, so when I'm working with a charged species, I do have to take into account that I've gained or lost electrons. So pause the video for a moment. Can you count out the number of electrons in a phosphate ion? Take a moment and do that. Okay. Well, when I did it, I ended up with 32 valence electrons. Where did that come from? 5 from the phosphorus. Each oxygen had 6, and there's 4 oxygens, so that's 24 plus 5. Plus, I've got that -3 charge, so I have to have 32 valence electrons total. Okay, so let's think about our skeleton. I want phosphorus in the middle. It's a singleton. I'm going to put the oxygens outside because that is what makes sense. The oxygens are going to bond to the phosphorus. They don't bond to each other. And I've got 32 electrons. We're going to try and make a structure that follows the octet rule. So if I start with single bonds between the phosphorus and each oxygen, that accounts for 8 electrons. And that gives phosphorus an octet. But each oxygen, of course, only has 2. But if I put 3 lone pairs around each oxygen, it's going to take me a little while to draw them all in, but that's okay. I'm going to end up accounting for all 32 electrons. Each oxygen has 3 lone pairs or 6 unpaired electrons around it. Now, the other thing is that it is a polyatomic ion. So what we're going to do to show this is I'm going to draw it with square brackets around it, and I'm going to put the charge outside. And the reason I do that is for the polyatomic ion, that charge belongs to the whole thing, not to any one particular atom, but to the group. And so that's typically what we do when we write them. Now, if you look at the other half of the slide, I have the ammonium ion and H4+. Similarly, stop for a moment, pause the video. How many valence electrons are in the ammonium ion? Okay, well, I drew it earlier, and I wrote down that I had 8 valence electrons in this structure. Right? Again, we only care about the valence electrons. We're not worrying about inner electrons. Why 8? The nitrogen contributes 5. Each hydrogen contributes 1. There's 4 of them total, but I also have that +1 charge, which means I have to take an electron away. So that's a total of 8. So when I go to draw this structure, again, I'm going to put nitrogen in the middle. There's only 1 of it. I've got 4 hydrogens. They tend to go on the outside anyway, so we'll draw that. And I'm going to do single bonds between the nitrogen and each hydrogen. Hydrogen typically only forms 1 bond. And if I look, oh, that's 8 electrons, 2 for each bond. The nitrogen has 8 electrons. Each hydrogen has 2, and we're done, except that we still need to remember to put that square bracket in and put that charge outside because the charge belongs to the group. Excellent. Let's keep going. All right. Now that we've done some structures that obey the octet rule, let's go on and talk about exceptions to the octet rule, which are actually fairly common. We can have molecules with odd numbers of electrons. These aren't very common at all. There's really only a few well-known examples. But one example is nitrogen monoxide, which, by the way, is an important molecule in cell signaling. So if we go and draw a Lewis structure for this, there's no way to make it fully follow the octet rule because we end up with 11 electrons, right? There's no way around that. And so one atom simply cannot have an octet. I only have two atoms. I have a nitrogen atom next to an oxygen atom. And there's really just no way to make everyone have 8 electrons. I can do a double bond between the nitrogen and the oxygen and give lone pairs, 2 lone pairs to each, to the oxygen. That leaves me 3 more electrons. That's 2, 4, 6, 8. I've only got 3 more to play with. I can do a lone pair on the nitrogen and 1 lone electron on the nitrogen. That's really the best I can do. This actually is the preferred structure. And there's really no other good way to handle it because Lewis structures are all built around pairs of electrons. And if we have odd numbers of electrons, that simply can't be. So I thought I would mention that briefly. Another important exception to the octet rule are electron-deficient structures. We tend to see this for compounds with boron or beryllium as the central atom, where they don't often end up with 8 electrons around the central atom. It's possible to draw them in some cases, but that's usually not what we get. So if we think about boron trifluoride, all right, let's again start by counting electrons. There are 7 electrons from each fluorine, and there's 3 of those plus 3 from the boron, so that's 24 electrons. Oops, sorry. Went on too fast. I was trying to get to the pen. All right, so I have 24 electrons. All right, and if I put boron in the middle, it makes sense that the fluorine atoms would be outside it. Okay, so the simplest structure I can draw involves single bonds between the boron and the fluorine. Okay, well that gives me 6, which means I still have 18. So it's easy enough to put 3 lone pairs around each fluorine. All right, but if you look, boron ends up with only 6 electrons around its central atom, which is not ideal, but boron can do this. We see similar kinds of things with beryllium compounds. All right. You know what I've realized? We haven't had a lot of structures with double bonds. Oh dear. Let's we want to change that around. Okay. So, all right. Another common exception to the octet rule involves expanded octets, where we have more than 8 electrons around the central atom. We see this a lot with sulfur, and we see this a lot for phosphorus. Elements in period 3 and lower do get involved in expanded octets, and they are certainly capable of doing that. Okay, so how do we handle that? Well, you're not going to really realistically end up with more than 12 electrons around your central atom. It just gets too crowded. They start repelling each other too much, so 12 is about as high as it goes. But it's very common to see this with sulfur and phosphorus containing molecules. Other atoms can do it too. Some evidence suggests that empty d orbitals get involved in the bonding. That's been called into question. So we're not really going to worry about the why and more about can we draw these structures. Okay. So what you have to do is if you count and have extra electrons, beyond once you've put everyone in, all the electrons in, and every atom has a octet, any additional electrons can go onto the central atom if it's from period 3 or below. So let's do an example, all right, of a polyatomic ion that has a central atom. If we look at SiF₆², right, if you count electrons, we end up with a total of 48 electrons. I'll write that down for you just so you can see it. I can get my pen to cooperate here. All right. So we're going to put the silicon in the center because that makes sense. And we'll put the fluorines around it. But you can see as soon as I write down 6 fluorines, there's no way that I can have a bond between the silicon and each fluorine and not have more than 8 electrons around my octet. It's simply around my central atom. It's simply not possible. And so as soon as I put those single bonds in, I already have an expanded octet around my silicon. And then lone pairs around each fluorine, 3 lone pairs. That brings me up to my 48 valence electrons. You can't see that one very well. All right. All right. But this does give me 12 electrons around the silicon, which can happen. Now it is a polyatomic ion, so we're going to go back and put our square brackets, all right, because it's just, the way it's done. All right, let's go on and do some more practice. All right, CH₂Cl₂. All right, so if we count electrons, I've got 4 electrons from the carbon, 1 from each hydrogen, so that's another 2, plus 7 from each chlorine, so that's another 14. That gives me a total of 20 electrons. Oops. Jumped ahead, trying to get to the pen. It's just not cooperating. 20 electrons. Okay, so central atom is going to be carbon because if we have carbon, it goes in the middle. I'll put the hydrogens around. I've got 2 of them. I've got 2 chlorines. They're also going to bond to the central atom. And I want to make sure all my electrons get in. So 2, 4, 6, 8. Starting with single bonds is always a good place to start. And then that gives me 8 electrons. My carbon's satisfied. Each hydrogen is set, but the chlorines right now don't have enough electrons. I've got 12 more to go. 3 lone pairs around each chlorine, and then we'll be all set. Okay. And then on the other half of the slide, I have BeCl₂. Now, remember, beryllium compounds are often electron deficient. So let's draw this. So with BeCl₂, I'm looking at a total of 16 electrons. That's 7 from each chlorine plus 2 from the beryllium. So I'm going to put beryllium as my central atom and draw the chlorines on either side. And I just feel like spacing them out equally, but that's not required. That gives me 4 electrons. And then if I put 6 more electrons, 3 lone pairs, around each chlorine, right, that gives me all 16 electrons that are accounted for, but notice that beryllium's electron deficient. That can happen. Now, there's an alternative structure I could draw, but it's not favored because it involves double bonds. And chlorine doesn't normally form double bonds. All right. So we can technically draw a Lewis structure for this molecule that still has 16 electrons and has an octet around beryllium, but based on charge distributions, this one's not preferred. But it's possible. But I also realized we hadn't done much with double bonds, and I really wanted to fill that in. Okay. Let's look at another polyatomic ion, the chlorite ion, ClO₂-. And if you stop and count your electrons, right, it's another 20 electron species. All right. And I'm going to put the chlorine in the middle. All right. Now that's unusual because normally we've had chlorine on the outside, but there's only 1 chlorine atom and there's 2 oxygens. So it's more reasonable to put the chlorine as the central atom here. And that actually does represent what this is doing. If I just start with a single bond between the chlorine and each oxygen, that's 4 of my 20. I can then give an octet to each oxygen by putting 3 lone pairs around each oxygen. That only accounts for 16 of my electrons. Each oxygen now has an octet, but my chlorine is not satisfied, but I still actually have 4 more electrons, so I can do lone pairs on the chlorine, 2 lone pairs. Now it is a polyatomic ion, so our old friend, these square brackets, are back, and we'll put that charge outside. Okay, another fun little molecule to represent is the oxygen difluoride molecule, which is another 20 electron species. And if you don't believe me, go count electrons. But it's also got 20 electrons. This time I'll put the oxygen in the middle and the fluorines outside of it. All right. This is actually a really similar structure. All right. So I can do lone pairs around the fluorine, 3 lone pairs around each fluorine, single bonds between the oxygen and each fluorine, and then 2 lone pairs on the oxygen. All right. This is a neutral species, whereas the other one was an ion. All right. Let's do just a couple more examples. All right. Formaldehyde, all right, methanol is its formal name. H₂CO. All right. So if we look at this one, each hydrogen contributes 1 electron. The carbon's got 4. The oxygen contributes 6 valence electrons. So we are looking at a total of 12 electrons. Now, as before, when we're not sure what to put in the middle, start with carbon. So let's put carbon in the middle. We'll put an oxygen outside of it, and a hydrogen, 2 hydrogens outside the carbon. There's no indication that the hydrogens are attached to the oxygen here. I didn't write it in that way. So I'm going to, this is the skeleton that I recommend. So I can do a single bond between the carbon and the hydrogen. Right, that's 2 electrons. Another single bond between the carbon and the other hydrogen. That's now a total of 4 electrons. If I do a single bond between the carbon and the oxygen, I've used a total of 6 electrons, but I'm looking at my carbon going, that doesn't have an octet. And if I also then put 6 electrons around the oxygen, I still don't have an octet. So this would be a great situation to try a double bond. Right? So if I have a carbon-oxygen double bond, that gives an octet for the carbon, and that leaves me 4 more electrons, and they can go as lone pairs on the oxygen. All right, this is something oxygen actually does quite a bit, is with the double bonds. And then there's one last structure I'd like to do with you, SF₄. So if we count electrons for SF₄, all right, 7 from each fluorine, 6 from the sulfur, that's a 34 electron molecule. So if I draw that, I put sulfur in the middle, 4 fluorines around it, no problem. I can do lone pairs, let's start with single bonds. We always start with single bonds, 2, 4, 6, 8. And I can, so that gives sulfur an octet, and that gives, if I do 3 lone pairs on each fluorine, that gives fluorine an octet. That one does, it's hard to see, sorry. All right, so that's all fine, right? Everything looks great till I count electrons, and I realized I've only put in 32. Ooh, wait a minute. I've got 8, the sulfur's got an octet, each fluorine's got an octet, that's 32 electrons, but I have to have 34 electrons in the structure. The last 2 electrons need to go on the sulfur, which has an expanded octet. That's not immediately obvious from looking at just the formula, but when we go to draw the Lewis structure, that is what we see. All right, so I hope that you feel more comfortable drawing Lewis structures now and feel like you can draw Lewis structures for both polyatomic ions and molecules, and also that you feel like you can handle expanded octets and electron-deficient molecules and all those fun situations that show up. We'll talk another time.